All right, so today we're going to continue our discussion of spontaneous symmetry breaking of gauge theories. And last time we described spontaneous symmetry breaking of gauge theory classically, gauge theories classically. Today we're going to do that quantum mechanically. We're going to quantize it. So the review of last time, if there are any questions at any point, please do ask. Non-abelian gauge theories gave us interacting quantum field theories in the infrared, in particular in 3+1 dimensions. These theories have gauge bosons that are massless vector fields, and but when we look around in nature, we see massive vector fields, whereas massive vector fields have poor UV behavior. So spontaneous symmetry breaking gauge theories gives us a UV sensible way of constructing a low energy massive vector field mode that whose UV behavior is protected due to gauge invariance that exists at high energies. Examples of this are superconductivity and the electroweave theory. All right, so what we did was we started with a review of spontaneous symmetry breaking of global symmetries. So every time you have a spontaneous breakdown of a continuous symmetry, there are massless scalar fields. The currents are still conserved, but the ground state is not. That's what spontaneous symmetry breaking means, right? For every broken continuous symmetry, for every broken generator of your Lie algebra, there will be a corresponding massless scalar boson called the Nambu-Goldstone boson. For example, take the ON model. For example, here's O2 model, the Mexican hat potential. Take it to be the mass is positive, lambda phi 4 is negative, so that you could arrange for symmetry breaking, right? For this Mexican hat form. Now, you take this action, expand around the classical vacua. So this V is mu over square root lambda, which is the classical V prime of phi equals 0. And around that, there will be a mode of the scalar field, the VEC1 model that fluctuates in the direction, in the radial direction in this example. And then there are the modes that are n-1 degrees of freedom that are perpendicular to it. All right. So the action becomes a constant, expand around this, becomes a constant plus del mu of pi k squared. So this is the kinetic term for the pi mode, kinetic term for the sigma mode. There will be a mass mode for the sigma, and it has to do with the fact that when you have this, the radial mode, this is the radial mode, right? This curvature, the second derivative is mass, right? That's why it picks a mass mode. And the Goldstone bosons remain massless because they correspond to motion in the flat direction. Right? Massless means that V prime is 0, and the flat, that this is like a round thing, right? So perpendicular direction remains flat. So that's a Goldstone boson mode, or modes. All right, so this is the mass mode for sigma. Then there's a potential. The potential you will have the sigma cube term, sigma pi squared, sigma 4, pi squared, sigma squared, then pi 4 terms, right? So this is what you obtain. ON symmetry is spontaneously broken to ON minus 1. The continuous symmetry transformation was phi a going to phi a plus epsilon delta phi a, leaving potential invariant, right? Now, to the lowest order in epsilon, delta phi a, del v, del phi a has to be 0, right? Is that clear? Take a derivative with respect to del phi b, you get this equation that has to be 0. Now, at the minimum of the potential, this term is 0. This is the mass term. So MAB2 delta phi A has to be 0 at the minimum. So delta phi A at the minimum, if it's 0, it means that there is a symmetry respected in the vacuum. If it's not zero, it means that the symmetry is broken. If a generator A has a broken symmetry, delta phi A is not zero, therefore its corresponding MAB has to be zero. The MAB will have to have a zero mode, right? So that is precisely the this is a quick and dirty way of saying that to every broken generator, there corresponds a massless boson mode, which is the so-called Goldstone theorem. Questions? This is very, very important phenomenologically. I'm motivated. Well, okay. Yeah. We talked about spontaneous symmetry breaking gauge theories. Gauge theory, gauge transformations are not symmetries. So it doesn't really make sense to break the redundancy of the description, but gauge theories have non-local degrees of freedom. They have one form symmetries, and non-locality is reflected in long-range force, right? That's a massless gauge boson, 1 over r squared potential, for example, in the case of electromagnetism. Now, what happens is that when there is a phi A, the charged matter, acquires a VEV, vacuum expectation value, gauge symmetry, or sorry, gauge theory has spontaneous broken one form symmetry, which means that the interaction becomes short range. The interaction becoming short range is equivalent, in this case, to the gauge boson acquiring an effective mass, right? Effective mass means that when it tries to penetrate into a medium, it will fall off exponentially fast, right? That's why it's short range. An example of this was superconductivity. I just mentioned this very briefly. This is when in electromagnetism, in QED, you have you have charged fermions, right? And a photon. A fermion cannot acquire a VEV, but there are situations like in superconductivity where when a fermion pair, the so-called Cooper pair, can acquire a VEV, vacuum expectation value, this is an observable, and this spontaneously breaks the U1 gauge theory, the result of which is that photon acquires a mass inside the material where this has finite VEV, which means that the photon cannot penetrate that or dies exponentially fast. It has to avoid that. And that's just a statement that if you have some material that above some critical temperature is there's some magnetic field. Once it drops below the critical temperature, it becomes superconductor. There is some sort of vacuum expectation value for the Cooper pairs. Magnetic fields cannot penetrate this; they have to go around it. So superconductors repel the magnetic field, and this is another way of saying that the photon becomes effectively massless in this medium. Yeah.
This is the same thing as just saying linear potentially is Yukawa type. It's just a Yukawa type.
Not really. I'm not sure if you could say those words. I do not know. I do not know. I don't think that terminology is. Maybe there's a sense to. I do not know. Maybe there's a sense to make sense of it as a model like that.
Can you also consider psi
bar? Very good. Yes, psi bar is a different condensate, though. Psi bar is a different condensate. Yeah. All right. Let's. I'm tempted to say things, but it's outside of my comfort zone. So I'll tell you a little bit more about it offline when I fact checked what I want to say. All right. All right, I'll tell you. No, giving a VEV to psi bar is very different physically. The reason is that here your condensate, your Cooper pair is charged. What you would like is to have a scalar that's charged under your symmetry so that you have spontaneous breaking of the gauge theory. Psi bar is charge neutral. But you could give it a VEV, right? But it's a different story. It's essential that the Cooper pair has electric charge 2Q, 2 electric charge. All right, we talked about, in the past we said that word identities require that the photon to be massless. So what's going on here? We're claiming that the photon acquires an effective mass, but we still have a gauge. We have gauge redundancies, gauge invariance. So what's going on with the word identities? It turns out that the way around this is that, quickly reviewing what the argument was, the photon should have no transverse degrees of freedom. That means that Q mu contracted the 1pi diagram, which is the quantum corrections to the propagated of the photon, should remain 0, which means that the propagated 1pi diagram should be proportional to this, right? This projects out the transverse mode, and this is pi q. When you write it this way, then a simple resummation of the full one loop correction to the diagram, sorry, not one loop correction, the full propagator could be written this way, where pi q sits down here as a shift. You remember how this was derived, right? It's just a resummation of this plus this squared plus q, blah, 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 right? Now, in the past, we said that because this guy, pi of q, which is a result of a one loop calculation, does not have a pole as q goes to 0, that means that the pole remains at the same place at q equals 0, which means that the photon remains massless, because this would be a wave function normalization. However, if you happen to have a massless mode around, as is the case of the spontaneous symmetry breaking, then when they run in the loops, what they do is that they allow for a 0 mode here. Well, they allow for a pole here, which will effectively result in a massive photon. We'll come back to this when we discuss QED in 2 dimensions. Questions?
So in general, you have a gauge redundancy, which is equivalent to one-form symmetry. So whenever you break a one-form symmetry, you get a degree of freedom with mass.
So when you have a one-form symmetry, when you insist on a local description, you get the gauge boson, right? When you spontaneously break the one-form symmetry, then your gauge, the would-be gauge boson, becomes massive. In the description, when you're describing a theory with one-form broken symmetry, which has non-local degrees of freedom, in terms of you're forcefully writing down a local action for it, that local action would have to give a mass to the gauge boson.
So I know the toric code breaks a one-form symmetry. Do you have massive?
Yeah, so the toric, that's a little bit of a longer story. So the toric code is a discrete gauge theory. Can you feel in the between? Can you feel in between what is that an answer, or?
Yeah, there's no Noether's theorem really, or
correct.
any. Yeah.
I mean, every time when we're talking about the spontaneous symmetry breaking in the language of we said that to every broken Lie algebra generator that corresponds to 0 mode, over there it's just a discrete symmetry.
Yeah.
Right.
Okay.
Even more than that, like I think the toric code is a little bit more involved. Well, it's actually a little bit, in a sense, simpler. It's a non-dynamical thing. You have gone all the way to the infrared and you have vacuum degeneracy. So the theory is topological. It's not, the degrees of freedom, the Wilson loops we're talking about, they don't even depend on the geometry. They depend only on topology, right?
Yeah.
So, for example, we said in regular gauge theories where we have local degrees of freedom, if you have a Wilson loop, right, there will be new non-local operators associated with a region with non-trivial pi1, right? So these are brand new non-local degrees of freedom. But if they're topological in the sense that these operators exist every time the region has non-trivial topology. But the operator itself is not necessarily topological in the sense that if you vary, change it, right? It's not like the value of this is the same for all loops, right? The Wilson loops, we calculated them, right? They depend on the geometry of it. In the confined mode, the expectation value of the Wilson loop was proportional to the area, right? That's not topological. Yeah. So topological theories are a lot simpler.
Thanks.
Sure. Here, I mean, remember that here a topological theory simply doesn't have degrees of freedom, probably local degrees of freedom, right? Here we're talking about a theory with local degrees of freedom. Sometimes there are non-local degrees of freedom as well, but yeah, they could still be localized. Anyway, so I said this, every time there are massless mode in the Lagrangian, pi q will have poles at q equals 0. Pi q is the one loop correction to the photon or gauge boson propagator. And in these cases, it's possible for the gauge field to acquire a mass which is consistent with Ward identities or gauge invariance. We'll work out an example of this explicitly when we discuss QED in 2 dimensions. So there will be spontaneous symmetry breaking over there. Well, sorry, no, there won't be spontaneous symmetry breaking. When you calculate the vacuum polarization in QED in 2 dimensions, you require mass. The photon becomes massive. It's actually one of the only exact calculations we could do. We'll ever do in this course. All right. So we talked about, as an example to demonstrate spontaneous symmetry breaking, let's talk about billion gauge theory. This is a model where there you have a complex scalar that's charged under U1, right? So this goes back to what we were saying, psi, you need it to be charged, otherwise you will not get spontaneous symmetry breaking. Sorry, I lost the train of thought. Anyway, so we're going to give a expectation value of f to this complex scalar that we write as phi naught square root 2. These are solutions to classical equations of motion. I did not write what v of phi is, but you remember it hopefully. So it's a complex vector field. So here's the vev, and then the fluctuations I write it as phi 1 plus I phi 2. Right, and then phi 0 could, as a real parameter, could be viewed as the expectation value of h, phi 1. Sometimes I'll refer to this phi 1 as the Higgs field, and going forward, sometimes I write it as h in anticipation of its applications and electroweak symmetry breaking standard model. So this would be, sometimes I write it as h, phi 1 is Higgs, the Higgs field, and phi 2 is the would-be Goldstone boson. But be careful. We did say that there is a gauge. This is a gauge theory, right? This is not, there is no actual Goldstone boson. It's a mode that looks like Goldstone boson because you're describing it using redundant local degrees of freedom, right? As a matter of fact, there is a way of gauge fixing that completely gets rid of this mode. We said this last time, I'll repeat it, right? So this is not physical at all. That's but Higgs field is physical. So the Higgs mechanism is the spontaneous symmetry breaking in gauge theory that generates a mass term for the gauge boson. So what's the gauge transformation for this theory? It's a U1 gauge field, so phi going to e to the power of I alpha x phi phase. So when you expand it in terms of an infinitesimal gauge transformation in terms of the Higgs and the Goldstone boson looks like this. And then the gauge field is transforming this way, right? Just linearizing the gauge transformation. It's an infinitesimal gauge transformation. Good.
Can you say something about Elitzer's theorem?
A what?
Elitzer's theorem.
I don't know what that is.
It says that there's no non-zero expectation values for any operators that are not gauge invariant. So you can't talk about Higgs mechanism in terms of spontaneous symmetry breaking, but you have to reformulate
Okay,
it.
so for let's just go over what you just said. I don't know what the theorem is, but let me just summarize what I said. An operator that's not gauge invariant is not an observable. So physically, it makes absolutely no sense to talk about a VEF. The same
Yeah.
way that physically it makes no sense to give a VEF to a fermion. A fermion is not an observable, right?
Yeah.
You could write down such a thing, but it's nonsensical because it's not an observable. It's not describing physics. So that's the first part of it. We can give a VEF to the gauge, non-gauge invariant operator. Then what?
You have to reformulate this Higgs mechanism in terms of purely gauge invariant quantities to correctly talk about.
Correct. So what are the purely gauge invariant quantities in gauge theory? So they're either Wilson loops, right? Or they are these Wilson lines ending on charges, right? So if you are talking about spontaneous symmetry breaking, it would either have to be that the Wilson loop acquires a 1-point function, right? Or it will have to be that a pair of charge anti-charge connected by Wilson line require a 1-point function.
Okay.
Right? Sorry, I think no, it doesn't have to be like that. It could be also the local degree of freedom. I apologize. Like here. Phi. You could give a VEF to phi. Charge matter. You could have a charge condensate. Good. If it's a boson, because they can all sit on top of each other. All right, so here's the gauge transformation. Keep this in mind. We'll come back to this. All right. What we did last time was we said, okay, here's the action. Let's just expand it around this VEF. And this is, remember, sometimes I write this H, this is phi 1. It's Higgs. This is Higgs. This is the massive mode, right? Phi 1 is the mode that's massive. It's this guy. And phi 2 is the perpendicular direction, right? So there will be this term. There is V of phi, and then there is this term. Do you see where they come from, actually? All I'm doing is I'm expanding this term. Right? Phi 1, right? Phi 0 over square root 2 plus H plus I phi 2 expanded, and this is covariant derivative, so there will be a mu's popping up. This is that expression repackaged in terms of real quantities, right? Because the action is better be real. And this guy is real, right? So absolute value of it. Now, what is important staring at this action is that, well, there will be a kinetic term for H, right? That's coming from this squared. There will be a term which is phi 2 squared a mu. That's a 4-point function. Then there is a term which is del mu of H a mu phi 2 from the cross term. That is a 3-point function. Good. So those are interactions. These are all interactions. There is a kinetic term for phi 2. There is a mu squared. So this term is going to give a mass term to the gauge field. A phi naught squared is going to give you a phi naught is going to be a mass. There will be a term which is again H squared a mu squared, which is again interaction term. But there's also a term which is phi 2 a mu with a derivative. This is that term that we wrote this way, right? Or however I wrote it, phi 2 a mu. It's coming from this term, phi 2 del mu phi. So it's proportional to the moment. There's a momentum factor, right? And then the other one will be also a 3-point function, right? H, A mu phi 2. So if you're only looking at the kinetic terms, you'll find a mass term for the photon. You'll find a kinetic term for H, which ends up being massive because of the potential term. And then you're going to get the massless modes for phi 2. Those are the kinetic part. Last time when we discussed this, we said that, okay, so this is some sort of, this means that we haven't diagonalized the degrees of freedom properly, right? It means that the degrees of freedom are, the kinetic degrees of freedom are neither A mu or phi 2, it's a mixture of them, right? That's what the way we described it last time. But this is a gauge theory. I'd already told you that phi 2 is, we could completely get rid of phi 2 using the so-called unitary gauge, and we'll be left with Higgs field. Here now it's beneficial to play a different trick, to use an arc-C gauge, right? You'll see why. What I'm gonna do going forward is to introduce an arc-C gauge to such that tuned exactly to remove this, and then it comes at the cost of introducing ghosts. So what happened in the U1 gauge theory when we did the arc-C gauge? And so what I'm building up towards quantization. Why do I want to do this? Because I want to quantize, right? This was what we did for Faddeev-Popov, right? In the U1 case, when we did the arc-C gauge, we got ghosts, but the ghosts decoupled because it came out of a change of variable that had to do with the arc-C gauge. It was a determinant of del squared. There was no dynamical field in it. So you could write this as an exponential of a bunch of ghost, anti-ghost, but they're not coupled to anything. You might as well just discard it. It comes out of the partition function. What we're going to see is that in the U1 gauge theory that has spontaneous symmetry breaking, if you use the arc-C gauge to eliminate this, your determinant Jacobian coming from Faddeev-Popov will depend on the fields. So there will be ghosts even in the abelian case. That's why I keep the arc-C gauge, because I want to quantize. That's going to be most of what I cover for the rest of the lecture. Okay? Is the idea clear? So last time we said in the unitary gauge, we could just completely get rid of this. You have a Higgs field. We're going to do a different description that's more appropriate for quantization. I don't know about more appropriate, but it's nice because it's a continuation of Faddeev-Popov. You're already familiar. Questions? All right. In quantization of abelian gauge theories, we saw that ghosts decoupled. This is no longer the case in spontaneous symmetry breaking. So how do I get rid of this term? What is this term? If you look at this term, I'm drawing it this way, but what this is del mu phi 2 E phi naught A mu. That's what it is. After an integration by parts, it looks like this. It looks like del mu phi naught. This is just a constant, right? Phi 2. Good. So maybe it's not quite clear yet, but this choice of, well, you'll see in a second that this choice of gauge is precisely, so remember in Faddeev-Popov, you introduce some gauge G. This is precisely what will cancel this term. We'll see that in a second, right? So we're tuning it such that it cancels. How? How does it happen? If this is your gauge, if you remember from Faddeev-Popov, the gauge, there was a gauge fixing term, which was e to the power of minus 1 over 2 cg squared. Okay, so let's put this squared of it. If you expand this, there will be 1 over 2 c del mu a mu squared. That's a familiar term. There will be a term from square of this, which is all gauge dependent because it's proportional to c. But then there's a term, the cross term, which has no c in it because this guy and this guy cancel. What is that term? It's E phi naught phi 2 del mu A mu, which is exactly this. So the gauge fixing term, if I make this choice, will precisely introduce in the gauge fixing term, there will be a term that will cancel this. Is that clear? Good. All right, so that's my gauge choice. What was the determinant? Where do the ghosts come from? You have a gauge choice. G of del mu A mu minus, what was it? C phi, oh, we forgot. E phi naught phi 0. Sorry, phi naught phi 2, right? What you do, if you want to calculate the, in the video above, what we did was that we first introduced G of alpha, which is G after a gauge transformation of the field. Then we took a derivative of that with respect to alpha, the determinant of which was the term of interest. Right? Okay, so let's do a gauge transformation. So what are the gauge transformation? Recall what the gauge transformations were. Delta H or phi, delta phi 1 is minus alpha x of phi, delta phi 2 is alpha x phi naught over square root 2 plus h, phi 1, and this is it. In this expression, right, there will be only this term, which will give you minus 1 over e del squared of alpha, right? If you recall, and then taking a derivative with respect to alpha, variation of alpha will give you minus 1 over e del squared. This term was precisely all that there was to it in QED, right? This term was the only thing that was in the Fedya Popov, so we just discard it. We take it out of the Lagrangian. Now what we obtain is that because phi 2 transforms this way, there will be, is delta phi 2 will be proportional to alpha, which after derivative, alpha goes away, phi naught over square root 2 plus h. There you go. Now, these are numbers, but h is a field. So h is now inside the determinant. Right? What was it in the non-abelian gauge theory? In the non-abelian gauge theory, it was, what was it? D mu del mu? Or the other way around, I don't recall, the other way around. Del mu d mu. Del mu d mu, which inside it has del mu d mu minus I, whatever, a mu. Yeah, there will be a g a. Okay. So over there, the ghost that came out of exponentiation of this were coupled to the gauge boson. Here, what are they going to be coupled to? Higgs. Right? So here's the ghost action. There's a kinetic term, but notice that this term is proportional to C. Right? So the gauge dependence is explicit. And the fact that the whole term, the interaction term, is proportional to C is a reminder for you that in an abelian theory, there is a gauge choice where you don't need ghost. This is just a matter of convenience. Good. However, in this particular choice of gauge, ghost coupled to Higgs, not the gauge field. The photon propagator is what you would expect. Did you expect this actually? Is the photon propagator familiar? Well, you could, I trust you could derive this. It's pretty straightforward. The only thing to be careful with is the massive. Now your photon is massive. Okay. Now, your Lagrangian density is now has this extra term, the gauge fixing term, that when you expand it, I'm just going to derive this actually, as a matter of fact. Well, I'm not going to derive it, but it's going to be in your face. It's pretty obvious. When you expand this, here's your Lagrangian, del A. So the kinetic term for A nu has this term. This is the old term that we had. And now this is the mass term for the gauge boson. Right? There's a kinetic term for Higgs. There's a mass term for Higgs that comes from the VEV, the minimum of the potential. Remember that. The mass of the Higgs field comes from the minimum of the potential. There is a mode, which is the Goldstone boson, quote unquote. And this term, which looks like a mass term for it, but is gauge dependent. So in this gauge, the Goldstone boson has a gauge dependent mass. There is no Goldstone boson. It's a gauge theory, right? This is just we're insisting on a local description, and the word Goldstone boson for us is just to keep track of things because we insist on a local description.
Sorry, what happened to the additional degree of freedom? Because we started with a complex scalar. It has two real degrees of freedom, and we chopped off one.
What was so 2 degrees of freedom in the real scalar? What else do you have in your theory?
The boson.
Gauge field. How many degrees of freedom do you have in 4D?
No, sorry, 2.
2, right? So because photon has 2 degrees of freedom, 2 polarization. So 2 plus 2 is 4. So here you have a Higgs, which is 1 variable. What else do you have? A massive vector field. How many degrees of freedom is that? 3. So people say that one of the scalar modes was eaten by the gauge field. Those words don't mean much. It's just this algebra. Describe this algebra. The electromagnetic, this propagator clearly shows you that the photons or electromagnetic field cannot propagate inside a medium where phi has acquired the expectation of VEV. Right? Is the analogy clear with so the superconductor is like you give locally, you give a VEV to the psi. Outside of your superconducting material, the VEV is 0. If the whole universe was superconductor, then that's the set that we're describing the Higgs field. There's a Higgs field everywhere in the universe. There's a condensate of it. Also notice that it's fair to say condensate of Higgs, right? Because at least in the way we described it, the real field was Higgs and the VEV was real. There's no nice way of separating them, but in this way of describing it, you could say the Higgs has a VEV. Again, that's not accurate terminology because the Higgs is really the propagating degrees of freedom on top of this vacuum. So maybe avoid that terminology. I don't think people use that terminology. I might have just made that up. All right, but we got rid of this mixing term by choice of gauge. Last time we didn't do this. What we did was we just diagonalized it. Right? We diagonalized the kinetic matrix, the mass matrix. All right, so what are the Feynman diagrams? The Feynman diagrams in this gauge, there will be the propagator for the photon, which looks like this. Now it's massive. And then there's just make sure you see where this comes from, this term. The Higgs, which has a mass. The phi2, which has a gauge-dependent mass. And then there is a ghost anti-ghost, which also have a gauge-dependent mass. The interaction vertex here with the ghost is only with phi2. Right? Questions?
psi equal to 1, then we can have a lossless.
I'll go over that. Yeah, I haven't fixed C yet. Where is that? Actually, somewhere in there I have a comment on it. But you're absolutely right. Yes. Oh, sorry. You want to fix C equal 1 so that this term goes away. Yes, you could do that. I'll comment on that. So we'll discuss 3 cases. Always with arc C gauge, there are 3 cases to consider. C equals 0, C equal 1. What else?
C equals infinity.
Yes. What does C equal infinity do? Just go back and we comment on this. You don't remember? Okay. Sorry. So next, we're going to talk about the non-abelian case. How am I doing in time? Okay, I think I have enough time. So in the non-abelian case, this is your non-abelian gauge theory Yang-Mills action. Now you have charged matter, right? Transforming some fundamental, for instance. Then there's some sort of interaction, self-interaction, potential for the charged matter. The gauge transformation of charged matter is like this. And the gauge transformation of the, well, and then the covariant derivative of the matter fields is this. Good? Now, if you expand the covariant derivative term, the kinetic term with the covariant derivative of the gauge of the charged matter, you're going to get just the derivative term. There will be IG A mu psi dagger del mu phi, sorry, phi dagger del mu phi minus this guy, which is the complex conjugate. Do you remember what this term was previously?
The coordinate just that's value.
It is a 3-point function, but it was an important term. Does this look familiar? What is this object? In the global case, hopefully this is familiar. The global case, phi del mu phi with the appropriate indices. Current charge to the gauge field, right? And if we recall, we looked at this, that we looked at the current conservation law, the matrix elements of it, right? That was one aspect of it that we discussed. And then there's this term. What is this term? This term looks like a 4-point function, but this term is the origin of the mass term for the gauge field. This is what makes the gauge field massive. When you give a vev to phi naught sits here, allowing for the mass term. Good? Can you follow every single term here? All right. Now what we're going to do is we're going to give a vev to the charged matter field. And then, of course, A mu is 0, right? These are solutions to classical equations of motion, right? I don't make things up. These are solutions to classical equations of motion. So it makes sense to expand around that. Now, there will be an MAB for the gauge field that's just coming from this term.
Maybe.
So
Yes.
previously, what was this? Previously, it was E phi naught, the whole thing squared. That was a mass term, remember? E phi naught, the whole thing squared, right? So this is that term. It's convenient to write it in terms of the anti-commutators to symmetrize it. Now, every unbroken generator means that TA phi naught is 0. The variation around the vacuum, right, is 0 for that. That means that there will be a 0 eigenvalue in MAB squared associated with that. This is precisely that quick and dirty way of doing Goldstone theorem. In the expansion of del mu phi j squared, we saw this term. This is the current coupling to this, right? Now, the current term, if you put phi naught, sorry. Now, there is a term which is one of these guys is phi naught, which means that you end up with a mu a ta del mu phi. What is that? It's a mixing of the gauge field with the scalar, the non-abelian version of this term. Good? You follow where the terms come from? All right. Now, next, what we would like to do is to spontaneously, we would like to quantize spontaneously broken non-abelian gauge theories. What would be the first step? You would like to, following what we just did before, you would like to pick an arc C gauge or some gauge. The strategy was to choose a fixed gauge fixing that removes the mixing, right? Why are we trying to remove the mixing? Once you remove the mixing, the kinetic term is standard. So what's the one loop correction to that? What's the effective action of one loop? It's just a bunch of determinants, right? We know how to, those calculations are straightforward. All right, so what is your GA? You have a GA now, I erased it. The gauge fixing is del mu a minus C omega of A of phi. I make omega of A the choice of gauge dependent on the field. Why? Because I have in mind canceling this term previously, exactly as we did before. Let's symbolically write it as F0A minus C omega A of phi. And I'm going to expand this, figure out what is the right value of F and omega to get this cancellation. All right. So where does this cancellation come from? Comes from the gauge fixing term, which is minus 1 over 2 C GA squared in the action. So it's going to be 1 over 2 C this guy squared. The term that's essential for us is the cross term, because it will have a factor of C from here, C downstairs, it will cancel. And this is what it looks like. It looks like FA omega A of phi. That is supposed to cancel this. Good? FA, F naught A, omega of A of phi, will have to cancel this term. So how do you get the cancellation to work? First of all, these terms are both in the action. So we could use integration by parts, right? F0A, if you recall, is just del mu A mu. You could use integration by parts to put the del mu on omega A with a minus sign. Now, this is supposed to be an integral of this expression. Can you see what it is? Omega of A has to satisfy this equation. Sorry, sorry. Omega of A, you could write it, this derivative, you could write it this way. Sorry, I said it incorrectly. So this derivative acting on this, you could write it this way, right? Now it looks like what you wanted. From this, you learn that del mu of phi dagger, del omega of A phi dagger plus this has to be equal to IG blah, blah, blah. Or omega of A is minus IG phi naught dagger TA phi minus phi dagger TA phi naught, which I can write as minus 2G imaginary of phi naught dagger TA phi. If you take a derivative del mu of this guy, what does it look like? It looks like the current, right? It would look like the lowest order contribution to current. Because if you take the current, which was phi dagger del mu, there will be schematically looks like this with appropriate TAs, right? If you put phi naught for both of them, it vanishes. Why? Because we took the background field to be independent of position. So that vanishes. Then the lowest order contribution to it is this. Good? Imaginary of phi naught dagger TA of phi. All right. So what is your Fedorov Lagrangian? It will be del mu of, well, what's your Lagrangian? Del mu of phi squared minus 4, the kinetic term. Sorry, the Yang-Mills term plus minus 1 over 2 c g of a squared. All right. Now I'm expanding phi around phi naught, and the fluctuation I'm calling chi. So here's going to be like d mu of chi squared, so kinetic term, plus g squared phi naught a mu phi naught, right? Oh, sorry. No, that's good. Yeah, no, that's good. That's good. This is a mass term for the gauge field. Here's a propagator in arc C gauge. And then there is the extra term, which is minus 2cg squared, imaginary phi naught dagger TA of chi squared. This is a gauge-dependent mass term for the quote-unquote Goldstone mode. If I focus on the kinetic term, it looks like this. This should look familiar. This is just a mass term. So a massive gauge boson, and here's the arc C gauge thing. The mass matrix is this. There's a mass matrix. In Fourier space, here's what the propagator looks like. The propagator, sorry, here's a two-point function. The two-point function looks like. The propagator is the inverse of this, which I write as an operator this way. Operator on A and B. A and B are the labels that run over dimension of G, right? It's a adjoint representation. The poles of the propagator carry the physical masses, eigenvalues of m squared. Now here is when we get to your question. Here's a propagator for the gauge boson, non-abelian gauge boson, spontaneous symmetry breaking. Spontaneous symmetry breaking. Let's pick 3 different choices. The unitary gauge is the gauge which is C equal infinity. Unitary gauge is the gauge that made phi 2 disappear. If you go back, you find that the mass of phi 2 was proportional to C. When you send C to infinity, phi 2 becomes infinitely massive. You cannot excite it. That's how it's discarded. Right? It's infinitely massive. In the Landau gauge, which is C equals 0, transverse gauge, this is what it looks like. Okay, maybe it's helpful to write it this way, right? So C going to infinity from this will give you m squared downstairs and p nu over m squared here with a minus sign, right? Here's what you get. C equals 0 is straightforward, right? This is what it is. And then C equal 1 is the Feynman gauge that drops the whole term here. It's proportional to eta mu. All right, questions?
the vacuum expectation value of the field of the Higgs field. It is measured, right? There's no way of, in this case, so you have to go out there and measure the
well, it's your vacuum. So sorry, the vacuum expectation value is set by the minimum of the potential. So if you know the potential, it's fixed.
The parameters of the potential are given by experiment.
Yeah, for sure. Viewed differently, what you have is a bunch of massive, we'll see it in Sandoval. You have a bunch of massive vector fields and a whole bunch of things. And there are these masses of a whole bunch of numbers. It turns out that if you write down this action, there are relations between these masses that are hard to see. But once we write down electroweak symmetry breaking, you'll see that all the numbers that come out of experiments are produced precisely using this formalism, and that is a success story for spontaneous symmetry breaking. That would be beautiful. Actually, that's an interesting story when we get to standard model. We'll see how all these numbers that you read off in experiments match, because these masses of things that come out in electroweak symmetry breaking, they're all going to be related by the vacuum of Higgs. They're all going to be decided by that, right? And then they match nicely.
That's why they discovered the Higgs boson was so essential.
Yeah.
If it wasn't there.
No, I mean, nothing can get mass. The gauge theory that's not spontaneously broken, it's hard to use this phenomenologically because it requires like a QED, right? That has to be a long range force. All right, ghost. Any other questions? Now, what happens with ghost? Remember where the ghosts come from? We made a choice of gauge. That gauge, sorry, there was a gauge fixing term. We make a gauge transformation in that, take a derivative with respect to a gauge transformation. Determinant of that is what you exponentiate and write it as a ghost term. All right, here are the gauge transformation. A mu transforms this way, covariant derivative of this. And here's how the charged matter transforms. You could derive this, it's pretty straightforward. dGA of del alpha B, because now alpha is also labeled by a generator of the group, Lie algebra. Looks like this. So this term, hopefully you recognize from non-abelian Yang-Mills, from Fedorov. The determinant of this what gave us the ghost boson. Sorry, the ghosts in Fedorov. And this means that the ghosts are going to couple. There will be a vertex, ghost, anti-ghost, gauge field vertex. This is sign of a non-abelian gauge theory that wasn't present in the U1 case. But now there's this extra term that couples in a gauge-dependent way, couples the gauge couples the quote-unquote Higgs to the ghost anti-ghost, right? So here's the ghost anti-ghost action. There will be a term, covariant derivative, that couples it to the gauge field, and then this is the extra term, right? There's a mass term, which depends on the gauge, and then there's a vertex with the boson, with the Higgs. Good questions. So now, in the case of the U1, I split the Higgs into Higgs. I wrote things as a Higgs plus the gauge, the Goldstone boson, right? But here I'm just writing everything in terms of chi, right? How do I distinguish the two? If you recall, in the unitary gauge, by sending C to infinity, we got rid of phi 2 completely, and we're left with the Higgs. if you that now there's an explicit scene here. So by sending C to infinity, you could like focus on various terms. But these are all gauge choices, right? The only thing that's meaningful is the number of degrees of freedom. In Fadiyah for pop, everything is gauge fixed. All right, questions? All right, and finally, here are the Feynman diagrams. The Feynman diagrams, the propagator for the gauge field is going to look like this. Actually, before writing the Feynman diagrams, it's convenient to define this TA phi naught with the appropriate labels. That's as FA. We're going to use this later. So why do we do that? So that we can write down the mass matrix as F transpose G squared. F is really the non-abelian version of phi naught, right? Which is gauge dependent, right? Because it carries the label A. This is the second derivative of the potential at phi naught. The propagator could be written as -1 over P squared minus G squared FF transpose, right? So you see already that the VEV squared gives a mass here. Remember this actually for electroweak signature breaking. The mass of the photon is decided by the charge squared times the VEV squared. Well, the mass is charge times the VEV, right? That's crucial. So the math of the in electroweak symmetry breaking, whether our gauge group is going to be SU2. How many gauge bosons are there for SU2 gauge theory? 3. They combine into W plus, W minus, and Z. There are 3 gauge bosons, and they have different masses. All the mass of these are fixed by their corresponding charges times the VEV of the Higgs. So they can't be arbitrary. They have to be related.
Why is it F transpose? It should be F transpose F.
No, I just wrote it. This is the way it comes out. Do the line of algebra is yeah, yeah. Huh?
F transpose, you treat as a scale.
No, it's not. F is a matrix.
Yeah, I mean, I see F as a vector.
Oh, you mean, sorry, in what? In what labels? The question in what labels? It carries F, carries a label A, which is the gauge generator label. What is the label I? This is the adjoint representation. I has to do with the representation of the matter, charged matter field. So if that's why the labels are different, right? If the charged matter field is in fundamental, then this is like a duplicated that. So this yeah, okay. This notation, you just have to play with it to.
I thought it was the ijth entry of the T matrix multiplying the jth.
No, I know it's a compact notation. Yeah. Yeah. Anyway. All right, so this is what it looks like. These are all the propagators, and oh yeah, remember that this is all sensible in the following sense that what is this term? This was the mixing between the gauge field and the gauge field and the boson is like this, and that's why the mass term we pick up is like this, right? We went over that last time. All right, so this concludes our discussion of spontaneous symmetry breaking of gauge theories, and by now, what we've seen is that in 4 dimensions we have these theories, which are well, first of all, exists gauge theory plus charged matter if the number of matter fields, fermions or other matter fields, is not too large, then that theory exists. Within the context of that theory, you could arrange for spontaneous symmetry breaking, and that the phenomenological consequence of that is gauge bosons that are massive and low energy. These are going to be the lessons that we need to model nature, standard model of particle physics, to describe the fundamental particles we see out there, right? So what we've been doing since the beginning of the gauge theory part has been about building four-dimensional models with the hope of describing nature for particle physics. Now, here's the thing. We had said before that scalar field theory in 4 dimensions doesn't exist. But now, what if you have a scalar that's charged under non-abelian gauge theory? So far what we discussed was gauge theory coupled to charged fermions. You could have charged scalars as well. How is the fate of that theory decided, whether it exists or not? You know exactly how to calculate that. Tell me what you would do. Sorry? Beta function at one loop. What's beta function at one loop decided by? What was the expression for it?
It was counter-terms.
We did a very quick and dirty way of deriving it at one loop. Do you remember? I gave you a master way of describing it. Effective potential. We did background gauge field method. We calculated effective potential. Then we saw you're going to get log of determinant of the kinetic term. And the kinetic term, we wrote the expression for what spin, representation theory of the Lorentz group, and what charge, representation of the gauge group, right? So you tell me what your matter field is, just put those numbers in, right? We literally calculate everything. The final expression for beta function, it was a bunch of numbers that we're adding up. Just put them in there. You put you want to build some theory like standard model of particle physics, you put the numbers in there, and the beta function hopefully comes out good. So this already tells you the following, that intuitively you could have this in mind. Charged fermions and the fact that scalar field theory didn't exist, the fact that fermions were in the QED itself didn't exist, had to do with the fact that the charged fermions and charged scalars have screening effects. Non-abelian gauge fields have anti-screening. So physically, the intuition is that without even doing the calculation, you know what the signs are. For any given gauge group, you have a budget of anti-screening, and then your matter fields, you have to use it wisely, right? Good. So that is the story. So by now, you know a large class of these theories. Now, what we're going to talk about next time, the next 2 lectures, are anomalies. So you might be tempted to right away jump into standard model and just describe standard model of particle physics, which is going to be a gauge theory that's spontaneously broken. That's successful. There is some subtlety. The subtlety is about symmetries and anomaly. Anomaly is a phenomenon that your classical action might have a symmetry. Quantum mechanically, the symmetry might not survive. How could it fail? What is on top of the action in quantum mechanics is a path interval. The measure of the path interval might not be symmetric. It means that you might not be able to regulate the theory in such a way that respects the symmetry. That's precisely bingo. So we're going to go over this. We're going to go over 2 things. We're going to start with scale anomaly. So we will go back to one of the most fundamental symmetries, ways of thinking about quantum field theories, which is conformal field theory, scale invariant theories, and talk about scale anomaly. Somebody hands you scale invariant theory. Are you guaranteed that if you put, scale invariant action, that you stick it inside the Lagrangian, are you guaranteed you're going to get a conformal field theory? Not at all. If you want to know why, take Yang-Mills. Yang-Mills in 4 dimensions is scale invariant. It's not a CFT. It's not conformal invariant. You want to know why scale invariant? What are the couplings of the theory? Yeah, it's dimensionless. We didn't use any dimension to write it down. If you didn't use any massive parameter to write down the classical action is scale invariant. Right? However, that's not a conformal field theory. As we saw, beta functions are non-zero. Right? So we're going to talk about anomaly. And then, so there will be 2 aspects of it. There will be anomaly associated with symmetries. And then we're going to discover that gauge theories might also have anomalies, which are nonsensical. Gauge anomaly means an inconsistency of the theory. You might have a scale anomaly, right? And that just means that your theory is not conformal scale, is not conformal. It's not scale invariant quantum mechanics. That's fine. But it makes no sense to have a gauge anomaly. If you have a gauge theory, it must be non-anomalous. We're going to talk about that. And the reason we go over this is that when we write down standard model of particle physics, a huge success story is to calculate anomaly for the gauge theory, gauge group, and see that it cancels. The number of fermions and the number of charged matter has to be fine-tuned so that the anomaly for the gauge theory is canceled. That will be important.
Otherwise, the theory goes to the trash bin.
At the level of this discussion, the theory goes into trash bin. Yeah. In flat space, the theory goes away, just disappears. There's some relevance to gauge anomaly and fancier context that I might, depending on whether we have time or not, I might or might not give you some examples of it. But yeah, so for the purpose of this conversation, if the gauge anomaly of standard model, there was no anomaly cancellation, standard model would have just thrown it out. All right. Okay. Questions? Not. Thank you so much.
Yeah, just one quick question.
Yeah.
In the homework, when I was calculating the